In our last few videos, we talked about the structure of organic molecules as represented by drawing Lewis structures, and here we're going to talk about the shape of organic molecules. Let's consider the shape or geometry of molecules, and here we have three examples. This is methane, CH4. Notice we have a central carbon surrounded by four groups. This is formaldehyde. We have a central carbon connected by three groups, and this is called acetylene. Each carbon is surrounded by two groups. To be able to predict the geometry, we're going to use the VSEPR model, which stands for valence shell electron pair repulsion. Valence shell electron pair repulsion. Now, this isn't a theory. This doesn't explain why. It's just a tool that we have that allows us to predict structure. Now, what exactly does this mean? Another way to think about this is that electrons hate each other. Remember, as we're drawing Lewis structures, each line represents a covalent bond, which is a pair of shared electrons. Well, let's think about this line representing a cloud of electrons. Here's another cloud, and another cloud of electrons. Because electrons have negative charge, these clouds hate each other, and they want to get as far away as possible. So because those negatively charged electrons repel each other, how can they get the furthest away from each other? If we look at our first example of methane, we have a central carbon connected to four groups. Now we have to think in three dimensions, not just flat, because if these are all in the plane of the paper, then these are 90 degrees away from each other, and that's as far away as they can get if they are in two dimensions. But instead, we need to think in three dimensions because that's what the molecule is going to do. So if we have our central carbon and we have two of those hydrogens are in the same plane, so the HCH are in the same plane, but then we have one hydrogen that is coming forward and one hydrogen that is going back. Now we have an overall tetrahedral arrangement, and our bond angles are 109.5 degrees. So much bigger than the 90 degrees if we were stuck in two dimensions. So when a carbon is connected to four groups, what we have is a tetrahedral arrangement. I just said carbon. When a central atom is connected to four groups, then we have a tetrahedral arrangement. In addition to this representation, there's a number of different representations we can use. We could kind of turn this on its side where we have one of those hydrogens straight up and in the plane and the other one down here. And then here's our hydrogen forward, here's our hydrogen back. And so this way we have something sticking up and then we have three legs on the bottom. So a few different representations that we can use. What's really important to keep in mind is that with respect to this central atom, we have two groups pointing up, for example, and two groups pointing down. Here we have two groups pointing toward the left. Here we have two groups pointing toward the right. So it's important to keep in mind that tetrahedral arrangement. If we look at our next example, formaldehyde, here we have a central carbon connected to three groups. These atoms are going to take on what's called a trigonal planar arrangement. The atoms are going to be all in one plane, so the carbon and the oxygen are in the same plane, the hydrogen and the other hydrogen are all in the same plane. And now we have bond angles of about 120 degrees. So whenever we have a central atom connected to three groups, think about a trigonal planar arrangement. And in our third example, where we have carbon connected to two groups, this is going to take on a linear geometry. We can rewrite it the exact same way it's already written. Focusing on this carbon, the angle between this hydrogen and this carbon is going to be 180 degrees. So they can be furthest apart from each other if they are pointing exactly in opposite directions. So 180 degree bond angle there, 180-degree bond angle over here as well. In general chemistry, you probably learned about a bunch of other shapes as well. When you have more groups of electrons, you have more to worry about. But for most of the molecules that we'll be talking about in organic chemistry, we'll be looking at a central atom connected to 4 groups, giving a tetrahedral arrangement, 3 groups giving a trigonal planar arrangement, or 2 groups giving a linear arrangement. Here we have a few more examples. Our first two, we have water, so we have oxygen connected to 2 groups and nitrogen connected to 3 groups. But we need to make sure we are starting with a complete Lewis structure, which means we need to fill in those lone pairs of electrons. Oxygen has 2 lone pairs, nitrogen has 1 lone pair. Now we can see that oxygen is connected to 4 groups, which means there will be a tetrahedral arrangement of electrons. Now the electrons have a tetrahedral arrangement, but you don't see that when you're looking at the atoms. And so we need to describe things differently, whether we are speaking with respect to all of the electrons or whether we're talking about the shape with respect to the atoms themselves. So let's say we want to redraw this. Let's put our oxygen here and let's put our lone pairs in the same plane, right? So on the last slide, as I was drawing methane, I had 2 hydrogens in the same plane, 1 hydrogen forward, 1 hydrogen back. So now let's have our lone pairs in the plane. That means that our hydrogens will be pointing down, but one will be forward and one will be back. Notice I'm using this wedge and dash notation. So this is supposed to use kind of an artistic perspective. So when we use the wedge, that means that this group is coming forward. So this is in front of the plane of the paper, and this one is going back behind the paper. So the carbon, hydrogen, hydrogen are in the plane. This is coming forward. This is going back behind. Here we have the lone pairs and the oxygen are in the plane. 1 hydrogen is coming forward, 1 hydrogen is going back. Now, another way that we could write this, if we have our hydrogens in the plane, that means that we have our lone pair, one is coming forward and one is going back. This is a little bit harder to draw, so let's just put in an itty bitty wedge with a lone pair going forward and an itty bitty dash with a lone pair going back. So because this central oxygen is connected to 4 groups, this atom, this atom, this lone pair, and this lone pair, the geometry or the shape is tetrahedral with respect to all electrons. But when we are just looking at the shape with respect to the atoms, so just focusing on HOH, then the geometry we say is bent. When we are thinking about a central atom with 4 groups, it will have a tetrahedral shape with respect to electrons. Rather than being the perfect 109.5 degrees that we saw in methane, which is the ideal for a tetrahedral shape, we can think about it as if the lone pairs take up more space. And so if this takes up a little more space and this takes up a little more space, these are going to be compressed a little bit. So that gives us a bond angle of about 105 degrees. So as we're describing the geometry of water, we can say that the arrangement is approximately tetrahedral with respect to all electron groups, but it is bent with respect to the atoms themselves. And this is very important, right? We have to remember that the existence of these lone pairs is going to have an impact on the shape of water. Next, if we look at ammonia, NH3, once again, we have 4 electron groups, hydrogen, 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 and a lone pair. So this will be tetrahedral with respect to electrons. But if we try to draw this, so let's say we have our nitrogen here, and then going straight up in the plane is our lone pair. Going down and to the left in the plane is one of our hydrogens, and then coming forward and to the right is a hydrogen, going back behind and to the right is another hydrogen. So with respect to all electron groups, it is tetrahedral. With respect to the atoms, this is called a trigonal pyramid. So when you are considering the shape of molecules where there is a lone pair or more on a central atom, it's really important that you take that into consideration because those electrons are going to impact the shape, but then you also have to remember what is the corresponding shape with respect to the atoms. In the case of water, we are tetrahedral with respect to all of the electrons, but bent with respect to the atoms themselves. With ammonia, this is tetrahedral with respect to all electron groups, and it is trigonal pyramid with respect to the atoms. So notice trigonal pyramid, not trigonal planar that we saw on the previous slide. Now, in our next example, we have multiple central atoms. So what we need to do is determine the geometry at each carbon. So if we look at our first carbon, this is connected to 4 different groups, and so this will be tetrahedral. If we look at our second carbon, it is connected to 4 groups, so this will be tetrahedral. If we look at our third carbon, this is connected to 4 groups. It will be tetrahedral. And our last carbon is connected to 4 groups. So guess what? This is also going to be tetrahedral. Now let's draw out this molecule thinking about the shape. And I'm going to start out with a zigzag of the atoms that are in the plane. So let's have a carbon connected to a carbon, connected to a carbon, connected to a carbon. These are all in the plane. And then let's include one of our hydrogens here and one of our hydrogens here. Next, if we focus on the first carbon, we already have 2 of our groups in the tetrahedral arrangement. So our other 2 groups are hydrogens. We're going to have one coming forward and one going back. On our next carbon, notice our 2 groups in the plane are going up. So now we have to draw our other groups going down and forward and back. In our next one, we already have 2 groups pointing down, so our other 2 groups must be pointing up, one in front and one in back. And for our last carbon, we already have 2 groups pointing up, so the other 2 groups will be pointing down, one forward and one back. We don't give a name to this entire molecule. It's not, tetrahedral or trigonal planar. Instead, we focus on the fact that each carbon is tetrahedral. Why does shape matter? Why am I asking you to be able to recognize or predict the shape of different molecules? Well, you can take my word for it that this is going to be important later on as we start talking about reactions, but there is an even more fundamental reason why we should care about this. And let's consider water versus carbon dioxide. So if we draw a Lewis structure for each of them, here is water, and here is carbon dioxide. Next, let's think about our bond dipoles. We know that oxygen is more electronegative than hydrogen, so there will be a bond dipole going this way and going this way. We know that oxygen is more electronegative than carbon, so we'll have a bond dipole going this way and this way. So with our bond dipoles, the difference between oxygen hydrogen is the exact same as the difference between oxygen hydrogen, so these bond dipoles would be exactly equal. The same thing over here, these bond dipoles are exactly equal. So if our bond dipoles are equal magnitude, opposite direction, then they're going to cancel each other out. So in the case of carbon dioxide, these bond dipoles will cancel, which means that carbon dioxide is overall nonpolar. Now, being nonpolar is going to result in having weak intermolecular forces. So intermolecular forces are the forces of attraction between molecules. So not within, but between molecules. If there's no dipole, it's weak intermolecular forces, and that leads to low boiling point, low melting point, which means that carbon dioxide is a gas at room temperature. So if the same was true for water, and this bond dipole cancels with this bond dipole, then we would expect water to have no dipole. It would also have weak intermolecular forces. It would also have a low boiling point, low melting point. So water would also be a gas at room temperature, which means life on Earth could not exist as we know it. So yes, shape is important. Let's think about the shape of both of these molecules. For carbon dioxide, the central carbon is connected to two groups, which means this is going to be linear. So the way I drew this Lewis structure also represents the geometry of this molecule. For water, however, the way I drew this Lewis structure does not reflect the actual shape. Let's represent the shape of water. So we can draw water like this. Let's imagine that our lone pairs, one of them is coming forward, one of them is going back. And so our hydrogen, oxygen, hydrogen are in the plane. Now let's draw the bond dipole. We have a bond dipole going this way and a bond dipole going this way. So now they do not cancel each other out because they're not going in directly opposite directions. Instead, these bond dipoles, because of the shape of the molecule, they add up to give a molecular dipole. Because water has a molecular dipole or a dipole moment, this leads to stronger intermolecular forces, higher boiling point, higher melting point, and therefore water exists as a liquid at room temperature. So we need to care about shape because a molecular dipole depends on both bond dipoles and shape. If a molecule doesn't have bond dipoles, then there will be no molecular dipole. If a molecule does have bond dipoles, it still may or may not have a molecular dipole depending on the shape. And we're going to talk more about this later, but the molecular dipole affects intermolecular forces, the forces of attraction between molecules, and then the intermolecular forces affects boiling point, melting point, solubility, a number of important physical characteristics. So let's look at a few more examples and try to determine whether the following molecules are polar. So we have methane, CH4. This is called carbon tetrachloride, and this is called dichloromethane. So let's start out by drawing Lewis structures. So here we have our carbon connected to 4 hydrogens. Here we have carbon connected to 4 chlorines, and we should include all of the lone pairs on the chlorines. And finally, here we have a central carbon connected to 2 hydrogens and 2 chlorines. But keep in mind, Lewis structures are only showing connectivity, so we could also write it like this, for example. So a couple of options, and there's other ways to show it as well, but this will demonstrate what I need to show you. Now that we've drawn our Lewis structures, next let's take a look at bond dipoles. So between carbon and hydrogen, there's essentially no bond dipole. So no bond dipole. In our next example, chlorine is more electronegative than carbon, so we have a bond dipole here, and here, and here, and here. And in our third example, no bond dipole between carbon and hydrogen, but we do have a bond dipole between carbon and chlorine. Chlorine is more electronegative than carbon, so the dipole arrow points toward chlorine. So next, let's think about whether the molecules have a dipole. Well, in our first example, because there are no bond dipoles, that means there is no molecular dipole. So we say that methane is nonpolar because there is no molecular dipole. Before we talk about this one, I'm going to skip ahead and let's look at this one. So if we were to consider molecular dipole, we could look at this representation and say that our bond dipoles are equal and opposite directions. Therefore, there is no molecular dipole, and so we would expect this to be nonpolar. But wait a minute, if I happen to draw it like this, then I would say that we do have bond dipoles and they're going to add up together to give me something like this. But does a molecular dipole depend on the particular representation that I've drawn? It shouldn't, right? Because these representations, these Lewis structures, are not giving us information on shape. They're just telling us that there are two chlorines and two hydrogens connected. All right, we have to think about the shape. So now I'm going to come back to carbon tetrachloride. We can redraw this taking into consideration the shape. So we have chlorine and chlorine and chlorine and chlorine. I'm not going to fill in the lone pairs because we don't need them in this case, and I already drew them before. So bond dipole, bond dipole, bond dipole, bond dipole. So our top two bond dipoles are going to add up together to give something like this. Our bottom two bond dipoles are going to add up to give something like this, but then these two are going to cancel. So carbon tetrachloride has no molecular dipole, which we would have gotten from looking at this, but it's more correct to address the molecular dipole taking into consideration the shape. Now, if we come back to dichloromethane, we could draw the shape like this. Here's a chlorine coming forward and a chlorine going back. We could write it like this with our chlorines up, our hydrogens down, forward and back. There are different ways that we could draw it, but as long as we are careful with our bond dipoles, we can see that we get a molecular dipole like this. Here, we have our bond dipoles giving us a molecular dipole that looks like this. So however we represent it, when we show the shape, and again, different representations of the shape are still going to lead to the conclusion that there must be a molecular dipole. So yes, we do have a molecular dipole. So you need to be able to tie together the concept of polar covalent bonds, where we talked about electronegativity differences, and shape to be able to determine whether a compound will be polar or nonpolar, whether it will have a molecular dipole or not, because that's going to be important for physical properties as well as chemical properties. We will come back to these concepts in a couple chapters and throughout the entire year of organic chemistry.